You ever find it tricky to explain exactly how something's moving? It sounds simple, but to really nail it, you need a specific set of tools. Well, that's what we're going to do right now. We're going to build your toolkit, giving you the 4 key ideas you need to perfectly describe any kind of motion, whether it's your daily commute or the path of a planet. Let's dive in.
All right, let's start with a simple question for you. Are you sitting still right now? I mean, your first instinct is probably, yeah, of course I am. You're not walking, you're not running. But the real answer is actually a bit of a head scratcher. Because the answer is, it totally depends on who's watching. You see, in physics, all motion is relative. It only makes sense when you compare it to something else. Okay, picture this. You're on a bus. To the person sitting right next to you, you're not moving an inch, right? You're both just sitting there. But to someone standing on the sidewalk watching the bus go by, you are definitely moving. See? Same you, same bus, same moment, but two totally different answers. And that gets to the absolute heart of this. To talk about movement, we first have to agree on a fixed point of view. And that right there leads us perfectly into our very first tool. Before we can even begin to track movement, we have to know where something is. And that all starts with what's called a reference point. A reference point, or you might hear it called an origin, is really just a fancy way of saying a fixed spot that we all agree on. It's the starting line. It's the "you are here" sticker on the map of, well, of everything. Without it, describing a location is basically impossible. Think about it. If I just say, the school is 2 kilometers away, that's not super helpful, is it? 2 kilometers from where? But if I say, the school is 2 kilometers north of the railway station, bam! Suddenly, it's crystal clear. The railway station is our reference point. Now we know the distance and the direction. We've pinpointed its position perfectly. Okay, so we've got our starting point locked in. Now we're ready for tool number 2. This is all about how you measure the journey itself. And it turns out there are 2 really different ways to do it. You can measure the path you actually took, or you can just measure the shortcut. First up, let's talk about distance. This is the one we all use every day. It's literally the total ground you covered, the total length of your path. If you wander all over a park, the distance is every single step you took. Think of it as the scenic route. But then there's displacement, and displacement could not care less about your scenic route. Nope, it only cares about one thing: the shortest straight line path from where you started to where you ended up. It is the ultimate shortcut. And trust me, these 2 measurements can be wildly different. Let's walk through a little journey to see exactly what I mean. Imagine an object starts at its home base, we'll call it point O, and travels in a straight line out to point A. So this first leg of the trip, from O out to A, covers a distance of 60 kilometers. Pretty straightforward, right? Ah, but hold on, the journey's not over. From point A, our object turns right back around and heads back the way it came, but this time it stops at a new spot, point C. All right, pop quiz time. Using our first measurement, what's the total distance this object has traveled? Remember, distance is the whole path. Okay, so it went 60 kilometers out and then came 35 kilometers back. You just add them up. The total distance covered, the entire scenic route, is 95 kilometers. But now, here's where it gets interesting. What's the final displacement? Remember, we don't care about the long journey anymore. We only care about the direct shortcut from the absolute beginning to the absolute end. So where did it start? At the origin, O. And where did it end up? At point C. The final position is just 25 kilometers away from where it started. So even though it traveled a whopping 95 kilometers, its displacement is only 25 kilometers. See the difference? It's huge. So let's just break that down. Distance is the grand total. Every bit of ground you covered. It's always going to be a positive number. But displacement, that's just the net change in your position. And get this, displacement can be positive, negative, or even 0. If you run a full lap on a track, your distance is 400 meters. But since you end exactly where you started, your displacement is 0. And that whole idea of direction, well, that is the perfect lead-in to our third tool. Because a lot of the time, just knowing how fast you're going isn't the full picture. You really need to know where you're going. This is where we get into the classic mix-up, speed versus velocity. Look, speed is just a number. It tells you how fast you're going, 50 kilometers per hour. Simple. But velocity is more specific. It's your speed plus your direction. 50 kilometers per hour, north. That's velocity. It's speed with a purpose.
and it's what pilots and navigators absolutely rely on. Okay, but let's be real. In the real world, things almost never move at one steady pace. We speed up, we slow down, we turn corners. To describe that kind of messy, real-world motion, we need our fourth and final tool, which is all about measuring change.
And that tool is called acceleration. Now, a lot of people think acceleration just means speeding up. But in physics, that's only part of the story. Acceleration is any change in velocity. So yeah, speeding up is acceleration, but guess what? So is slowing down. And so is just changing direction. If your velocity is changing in any way, you're accelerating.
Think about riding a bike. When you pedal harder to go faster, your velocity increases. That's positive acceleration. When you hit the brakes, your velocity decreases. That's negative acceleration. You might have also heard it called deceleration. Both are changes in velocity, and so both are types of acceleration. And just like that, you've got it. Your complete toolkit for describing motion. You start with a reference point to establish a position. You measure displacement to find the direct change in that position. You calculate velocity to find out how fast and in what direction that position is changing. And finally, you use acceleration to describe how that velocity itself is changing. And here's the really amazing part. These four simple tools don't just describe a trip to the grocery store. They are the very same concepts scientists use to map the orbits of planets, to track the paths of stars, and to understand the grand cosmic motion of entire galaxies. All of it, from the smallest movement to the largest, starts with these fundamentals, knowing where you are and where you're going.